Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to continue our lecture on fluids, and we've made it to the second objective, which is titled hydrostatics. Hydrostatics is a branch of fluid mechanics that deals with fluids at rest and the forces and pressures exerted by these stationary fluids. When we talk about hydrostatics, we're primarily interested in understanding how pressure is distributed through a fluid and how it interacts with the walls of its container. To start, we want to first focus on Pascal's principle. This principle states that when an external pressure is applied to an incompressible fluid, the change in pressure is transmitted uniformly throughout the entire fluid and to the walls of its containing vessel. Now, as a reminder, an incompressible fluid is a fluid whose volume doesn't change significantly under pressure. So in short, Pascal's principle states that any change in pressure applied at one point in the fluid will propagate undiminished to every other point in the fluid. So imagine this scenario. Let's say we have a sealed, unopened carton of milk. If we were to press down on one side of the carton, the pressure that we would apply would not just affect the part of the carton we're pushing on, it would be transmitted throughout the entire milk carton. Because the milk inside is incompressible, every part of the milk experiences the same increase in pressure. Now, if we suddenly open the cap, that built-up pressure is going to cause the milk to shoot out. And this is Pascal's principle in action. The pressure we applied was distributed evenly throughout the fluid. Now, one of the most remarkable applications of Pascal's principle is in hydraulic systems, which use the near incompressibility of liquids to generate mechanical advantage. Remember that mechanical advantage is the ratio of the output force to the input force in a machine, allowing a smaller input force to move a larger load. These hydraulic systems, they're used in a variety of machines, from car brakes to heavy construction equipment like cranes and bulldozers. So let's take a closer look at how a simple hydraulic lift works. In this system, we have a closed container filled with an incompressible liquid, typically an oil. There are two pistons, each with a different cross-sectional area, and they're connected by a fluid-filled chamber. Now, on one side, we have a small piston with a cross-sectional area of A1. When a force F1 is applied to this piston, it moves downward. It moves downward, pushing the liquid below it. Now, since the liquid is incompressible, this displacement generates a pressure within the fluid. Now, according to Pascal's principle, this pressure is transmitted undiminished throughout the entire fluid. That means the same pressure reaches the other side of the lift, where we have a larger piston with a cross-sectional area A2. Because the area of the larger piston A2 is greater than that of the smaller piston A1, the force F2 that is exerted by this piston will also be larger, even though the pressure is the same. And this is because pressure is force per unit area. For the same pressure, a larger area results in a larger force. So in essence, the hydraulic lift allows a small force applied to a small piston to be converted into a much larger force on a larger piston, enabling the lift of heavy objects with relatively little effort. The ratio of the forces, this is directly proportional to the ratio of the cross-sectional areas of the two pistons. This is the mechanical advantage that's provided by hydraulic systems. Now, you might be wondering, does this system violate the law of conservation of energy? After all, we seem to be getting more force out than we're putting in. But in reality, there's no violation. What's happening here is that while the force is amplified, the distance over which this larger force acts is reduced proportionally. We can further prove these points by working through things mathematically, as is shown here. Ultimately, this serves to demonstrate that the work done on the smaller piston is transferred to the larger piston. Therefore, one needs only to exert a small force over a small area through a large distance to generate a much larger force over a larger area through a smaller distance. Keeping that in mind, let's go ahead and jump into a practice problem. This problem says a hydraulic press has a piston of radius 5 centimeter, which pushes down on an enclosed fluid. A 50 kilogram weight rests on this piston. Another piston in contact with this system has a radius of 20 centimeters. Taking that the acceleration due to gravity is equal to 10 meters per second squared, what force is needed on the larger piston to keep the press in equilibrium? To solve this problem, we need to remember that pressure is equal to force divided by area. And here specifically, we're going to need to use Pascal's principle. This states that the force of piston 1 divided by the area of piston 1, this is going to be equal to the force of piston 2 divided by the area of piston 2. And it's this equation right here that we're going to be using to solve for what force is needed on the larger piston to keep the press in equilibrium. We are solving for F2. So we can go ahead and rearrange this equation to solve for F2. And we can do that by multiplying both sides by A2. This is the area of the larger piston. What we get then is that the force on this second piston is equal to the force on the first piston multiplied by A2, this is the area of the second or the larger piston, divided by the area of the first. Now here we're dealing with a hydraulic press that has a piston of radius 5 centimeters and another one with 20 centimeter radius. What we're dealing with is a circle. So when we talk about the area of a circle, we're talking about pi r squared to calculate that area. And we can use that to replace these terms here. So now we can write that F2 is equal to F1 multiplied by pi r2 squared divided by pi r1 squared. What we notice here really quickly is that there's a pi in the numerator and there's a pi in the denominator, so they cancel out. Now what we have is the force of piston 1 multiplied by r2 squared divided by r1 squared. We're not directly given the force for piston 1, but we can calculate it because we know that force is equal to mass multiplied by acceleration. So we can rewrite this once more to be mass of piston 1 multiplied by the acceleration, and here that's going to be the acceleration due to gravity. And this is multiplied by r2 squared divided by r1 squared. Now this form of the equation we can use because we now have all of the necessary variables. In this form of the equation, we can start to plug things in. We know that the mass of piston 1 is 50 kilograms. The acceleration due to gravity is 10 meters per second squared. And then here we have the radius of piston 2, which is equal to 20 centimeters. That's squared, and it's divided by the radius of piston 1, which is equal to 5 centimeters, and that's also squared. Now, let's go ahead and start working through the math here. Let's start with everything that's inside these parentheses and do the squaring. So 20 squared, that's equal to 400, and 5 squared, that's equal to 25. Then out here we have 50 multiplied by 10, that's equal to 500. Now 25 and 500, they're both divisible by 25. So we're going to divide both values by 25. This gives us 1 over here, and that gives us 20 over here. Now what we're left with is 20 multiplied by 400, and this gives us 8,000. And our units here are going to be newtons. So the force that is needed on the larger piston to keep the press in equilibrium is 8,000 newtons. Next, we want to discuss Archimedes' principle. Archimedes' principle is another important concept in physics that helps us understand the phenomenon of buoyancy. This is the upward force exerted on an object when it is submerged in a fluid, whether liquid or gas. This principle is essential for explaining why objects float or sink, and it's named after the ancient Greek mathematician and scientist Archimedes. The story goes that Archimedes was tasked by the king to determine whether a goldsmith had replaced some of the gold in the royal crown with a cheaper material. The king wanted to make sure he was getting what he paid for, and he wanted to verify the purity of the crown without damaging it. While pondering this problem, Archimedes experienced his breakthrough during a bath. He noticed that as he immersed himself in the water level rose, and he realized that the volume of water displaced by his body, that was directly related to the volume of his body. This observation led him to formulate what we call now Archimedes' principle. This principle states that any object fully or partially submerged in a fluid experiences an upward buoyant force equal to the weight of the fluid displaced by the object. In simpler terms, the fluid, quote unquote, pushes back against the object with a force that is equal to the weight of the fluid that the object displaces. So for example, when you place an object in water, it displaces a volume of water that's equal to the submerged volume of the object. The water that is displaced exerts an upward force against the object. This upward force is what we call the buoyant force. Now, the magnitude of this force, it depends on the density of the fluid, the volume of the fluid displaced, and the acceleration due to gravity. And so it can be described mathematically. And here what we see is that this force, again, is equal to the density of the fluid multiplied by the volume of the fluid displaced by the object multiplied by the acceleration due to gravity. And this is equal to the density of the fluid in which the object is submerged multiplied by the volume of the part of the object that's submerged in the fluid multiplied by the acceleration due to gravity. Keeping this in mind, let's discuss what this means. This force, this buoyant force, this is always directed upwards. It counteracts the weight of the object submerged in the fluid. So if this force equals the weight of the object will float. If it is less, then the object will sink. So one way to visualize this force is to think of it as the fluid trying to return to the space it originally occupied before the object displaced it. The fluid exerts an upward push on the object to regain its space, which is why the buoyant force is directly upwards. Now we want to ask a really important question. How can we determine how much of a floating object lies below the surface? Whether an object floats or sinks, that depends on the relationship between its density and the density of the fluid. If the object's density is less than that of the fluid, it will float. This is because the object only needs to displace a relatively small volume of fluid to generate a buoyant force equal to its weight. So for example, a piece of wood, it floats on water because its density is lower than that of water. It displaces enough water to balance its own weight and then stops sinking. On the other hand, if the object's density is greater than that of the fluid, it will sink. In this case, even when the object is fully submerged, the volume of fluid displaced does not generate a buoyant force that's sufficient to counterbalance the object's weight. A gold crown, for example, that would sink in water because gold is much denser than water, meaning the crown would need to displace a volume of water far greater than its own to stay afloat, which isn't possible given its size. So to make sense of this, in short, we can use Archimedes' principle to determine how much of a floating object lies below the surface. And this is often done by comparing the densities of the object and the fluid. If the object's density is less than that of the fluid, we can calculate the percentage of its volume that's going to be submerged. This percentage corresponds to the ratio of the object's density to the fluid's density. So for example, if an ice cube with a density of 0.92 grams per cubic centimeter is placed in water which has a density of 1 gram per cubic centimeter, it will float with about 92% of its volume submerged because its density is 92% that of water. So in summary, Archimedes' principle not only explains why objects float or sink, but it also gives us a way to calculate the buoyant force and predict the behavior of submerged and floating objects. With that, let's go ahead and tackle a practice problem together. This problem says a wooden block floats in the ocean with half its volume submerged. Find the density of the wood, and note that the density of seawater is equal to 1,025 kilograms per cubic meter. Now we start by recognizing a key concept. The weight of an object must be equal to the buoyant force when it is floating. This force is the upward force that's exerted by a fluid, in this case seawater, that allows the block to stay afloat. Now, the first thing we want to do is we want to recognize that the weight of the block, that's given by its mass multiplied by the acceleration due to gravity. And that is equal to the density of the block multiplied by the total volume multiplied by the acceleration due to gravity. So therefore, the weight of the block is equal to this term right here. Next, the buoyant force, this is the weight of the displaced water. It depends on the volume of water displaced. Since only half of the block is submerged, the volume of displaced water is going to equal the volume of the block divided by 2. So the buoyant force is going to be for water equal to the density of water multiplied by the volume of water, which we just said is equal to the volume of the block divided by 2. and that's multiplied by the acceleration due to gravity. Now what we can do is we can set these two terms equal to each other. So we can say that the density of the block multiplied by the volume of the block multiplied by the acceleration due to gravity, that's equal to the density of the water multiplied by the volume of water, which is equal to the volume of the block divided by 2. And that's multiplied by acceleration due to gravity. Now, what we notice is that the acceleration due to gravity term appears on both sides, so we can cancel them out. In addition, we notice that the volume of the block also appears on both sides of this equation, so we can cancel that out. What we're left with is that the density of the block, that's equal to the density of water divided by 2. The nice thing is that we're given the density of seawater. It's equal to 1,025 kilograms per cubic meter. We're just dividing that by 2. And that's going to give us 512.5 kilograms per cubic meter. So the density of the wood is equal to 512.5 kilograms per cubic meter. Now, the last topic for this second objective is going to be molecular forces in liquids. Here, we're going to discuss 3 properties that are indicative of the intermolecular attractive forces holding molecules together in the liquid phase. And those are surface tension and capillary action. Let's go ahead and start by discussing surface tension first. This is a fundamental property of liquids, and it's defined as the energy required to increase the surface area of a liquid by a unit amount. Surface tension occurs because molecules at the surface of a liquid, they experience fewer intermolecular forces than those in the interior. Inside the liquid, molecules are surrounded by others on all sides, leading to balanced forces and lower potential energy. In contrast, surface molecules are only partially surrounded, so they experience a net inward pull from the molecules beneath them. As a result, the surface of a liquid tends to contract and minimize its surface area, creating an effect similar to an elastic membrane. This is why water droplets form nearly spherical shapes. A sphere has the smallest possible surface area for a given volume. Now, the strength of surface tension, that's directly related to the intermolecular forces within the liquid. So, for example, water has a high surface tension due to strong hydrogen bonding between its molecules, which is why small objects like a needle can sometimes float on its surface without sinking. Now we want to talk about capillary action. And in talking about capillary action, we're going to discuss cohesion, adhesion, and the meniscus effect. Capillary action, this is the spontaneous movement of a liquid through a narrow tube or porous material against the force of gravity. And this occurs due to the combined effects of cohesion and adhesion, which are both types of intermolecular forces. Now, cohesion. This refers to the attractive forces between molecules of the same substance. In liquids, these are the forces that hold molecules together, like hydrogen bonds in water. Cohesion is responsible for the surface tension of liquids, and it contributes to the rounded shape of liquid droplets. Adhesion, on the other hand, this is the attraction between molecules of different substances. So, for example, water molecules are attracted to the glass surface of a tube due to adhesion. When adhesion is stronger than cohesion, the liquid is drawn up the tube, leading to capillary action. This is seen in how water rises in narrow tubes, or how plants draw water from their roots to their leaves. Now, this leads us to discuss the meniscus. This is the curve that's observed at the surface of a liquid in a container, and it results from the balance between cohesive and adhesive forces. In a concave meniscus, what we see here is that adhesion to the glass is stronger than cohesion between water molecules. This is seen with water in a glass tube, and this causes the liquid to climb up the sides of the container. In contrast, a convex meniscus, this occurs when cohesion is stronger than adhesion, as seen with mercury in glass where the liquid curves downward. So let me repeat that one more time. In a concave meniscus, adhesion to the glass is stronger than cohesion between water molecules, causing the liquid to climb up the sides of the container. In contrast, a convex meniscus occurs when cohesion is stronger than adhesion. Capillary action is essential then in many natural and technological processes. In plants, it enables the transport of water and nutrients from the soil through the tiny xylem tubes. In everyday life, capillary action is observed when a paper towel absorbs a spill, or when ink moves up the nib of a fountain pen. In summary, the properties of liquids, surface tension, and capillary action, they're all interrelated and they're governed by the behavior of intermolecular forces. Surface tension arises from the cohesive forces at the liquid surface, leading to minimized surface area. And on the other hand, capillary action demonstrates the interplay of cohesive and adhesive forces. And with that, we've completed all of the topics in Objective 2. In the next video, we're going to continue with Objective 3 and 4. I hope that this has been helpful so far. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.